Hi, I'm Tom O'Donnell. My disclosure is I work for Siemens Healthineers. Uh, for my talk, so we're discussing this Smith-Bindman paper. And I'm not going to answer the question, based on this paper, should or shouldn't someone get a CT? I'm assuming you're getting that CT. And how can we make the CT have the lowest dose possible while still maintaining diagnostic image quality? So in my talk, I'm going to talk about how radiation dose has been going down over time. And I'm going to show some examples of very nice low dose images showing that we are achieving this. I'm going to talk about how we do this, the technologies that we use to lower the dose. And I'm going to talk about the future. What are some of the potential technologies that are available to reduce the dose even further? Okay, so here we have, I plotted over time, over about 20 years, the manufacturer's recommended dose for lung screening. In this case, the manufacturer's Siemens. And as you can see, from like around 2003 to more or less the present, the CTDI, the dose, has halved over 20 years. That's a significant drop. And now our recommended dose is about 0.84 CTDI. It's a little high. We want to make sure that there is a diagnostic scan, but you can go lower. And here is an example of a 0.55 milligray scan. And you can see this is, very nice image quality. You can really see things very clearly. So we are able to get quite low. We can get even lower. So here's an example of like some serious scraping. Where on the right, we have an effective dose of 0.13 millisieverts, about 0.24 CTDI, where, yes, this is noisy, but you can still see the lung nodules. Now, in this paper, they used LungCAD as a kind of a objective metric to determine whether you can locate the lesions in the standard dose as well as in the ultra low dose. And you can see that you can find in their conclusion is that CAD of solid pulmonary nodules using ultra low dose CT with chest X-ray equivalent, really, really low radiation dose has similar sensitivities to those with standard dose CT. Okay, I'm going to talk about dose reduction technologies. The first one was just discussed, so I'm going to go over this quite briefly. Deep learning is in our lives everywhere now, and it's also in image reconstruction used for artifact reduction, super resolution, as well as noise mitigation. And here's an example where you have, let's see, here's when we use the. So here we have standard iterative reconstruction at a conventional iterative reconstruction at a standard dose. This is standard iterative reconstruction at a low dose. You can see it's quite noisy, but if you employ deep learning iterative reconstruction, which has been quite successful, if you look at the literature, you can get a really nice dose, and you can get a super low dose with a very nice looking image. Moving on, spectral filtering. So this is the here we go. Right, here we go. So this is your X-ray tube. There's a standard bow tie filter. You can add an additional filter. In this case, it's silver, but it can be tin. And you can see from the profile of the histogram of the photons coming out that this additional filter really cuts away many of the low energy photons. And what it does is it makes the beam more dose efficient. That is, the photons that have reached the patient are more likely to make it to the detector. And you can see this results in a really significant change in dose. So This is not a lung screening. This is more like us looking for cysts. But you can see here on the top where we have kind of a standard dose. And then with this additional filtering, spectral filtering, you really kind of, these are very nice looking images, and you're reducing the dose significantly to the patient. Photon counting was mentioned already. In this study, I will say that not only does the dose decrease as compared to standard conventional energy integrating CT, but the noise also decreases, and the measurements, more subjective measurements of sharpness and image quality were found to be significantly better. Okay, so let's see here. Okay, patient positioning with a 3D camera. So the tube current modulation technologies that reduce the dose of the patient depend on that the patient is properly isocentered in the gantry. If, for example, the patient is too high, too close to the X-ray source, when you create your scout, your topogram, the patient may appear larger than they actually are. So the tube current modulation software will assume, okay, I have a bigger patient. I have to increase the dose to make sure that I get adequate image quality, and the patient becomes overdosed. And here's a kind of a picture. That's the patient. That's the X-ray tube, and we want the patient to be perfectly isocentered. So in this study, we looked at comparing centering by automatic means by the camera versus the technologists. And we found that the camera was more consistent in terms of isocentering the patient. It was faster, and as a very nice bonus, it also decreased the dose on average between these two cohorts. Okay, so potential future technologies. So the technologies that I just described, these are either in place or in development by almost all the vendors. There are potential future technologies that are being looked at. For example, scoutless, by scout, I mean like a topogram, the initial X-ray you take before the CT scan to kind of plan the scan. Scoutless scanning is now being seriously looked at, and I think it's even happening in China, where you use, for example, a 3D camera to figure out the scan range and plan your scan. So get rid of that, although small, you don't even need that extra radiation from the topogram or scout. Another technology that's being looked at is sparse reconstruction. We're borrowing this from MR. So MR has had great success in sampling the K-space to and use sparsity to reconstruct without using all the data that's available. And it's kind of, they're really pushing past Nyquist with this. People are looking at doing that with CT. It's a little more challenging in that instead of using all the views from 360 degrees, you only use some of those views. And the ideas are the same. The challenges are how to remove those views without damaging the image quality. Simultaneous multi-contrast scanning. This is possible with photon counting CT, where you can have two different contrast agents at the same time. So imagine you don't have an arterial scan and a venous scan. You have a simultaneous arterial venous scan, and you can see both simultaneously with different colors. And finally, we can look at fast MA adaptation X-ray tubes, where we're doing a better job with the tube current modulation by being more precise. So in conclusion, radiation doses have been getting lower over time, and we should expect this trend to continue. Thank you.